Howdy, everyone. My name is Eli Norris. I'm a second-year PhD student in the Department of Materials Science and Engineering at Texas A&M University. Today, I'm going to be giving a literature review on the article titled "A Simple Method to Construct Process Maps for Additive Manufacturing Using a Support Vector Machine." This article was published by Wang Aoyagi in the Journal of Additive Manufacturing in 2019, and this research comes out of the Institute for Materials Research in Tohoku, Japan. So, what did the authors do? So, the idea of this paper is to take a common biomedical alloy that's cobalt chromium and additive manufacture it using electron beam technology. And this is a very common additive manufacturing technique. And the way it works is you have an electron beam or an electron gun that generates an electron beam, and you have electromagnetic lenses that you can use to focus this electron beam, which is shined onto a build plate which has powder spread across it by rollers. And then you subsequently scan the regions that you want to fuse together according to the CAD model, and then drops the build plate by your layer thickness and rolls on another layer. And then you build the part from the bottom up in this additive technique. And the challenge with these additive techniques is there are many process parameters associated with electron beam additive manufacturing. You have the current, the scan speed, your focus offset, your hatch spacing, layer thickness, the speed function. All of these are variables that can be tuned, and tuning these will change the microstructure and the mechanical properties of the associated fabricated part. And this is the most tedious and time-consuming part of additive manufacturing, is the process parameter optimization phase. So the authors propose a machine learning model that uses an SVM to classify prints as either good or bad based only on the surface quality, taking an image of the surface after it's printed. And the reason they can do this is, if we take a look at this figure, you can see if we have high energy of the beam during melting, we get very deep penetration into the previous layer. And it creates this keyholing type porosity. And then when you rake across a layer of powder, powder infills these cavities, and then you remelt it. And during melting and printing of the associated next layer, you're unable to melt these powder particles that are trapped within these pores. And this is lack of fusion, keyholing defects, and it's not net shape at all. Whereas if you have too low of energy, you won't have as deep of penetration into the previous layer, but you're not fusing all of the powder particles together. So when you print the next layer, you still have some powder particles that are unmolten because you didn't have sufficient energy to fuse them together. And when you have optimum energy, you melt all of them in a nice clean layer. And this is how we can tell from looking at the surface what's going on inside the material. So they trained a support vector classifier to, based on looking at the surface, classify the print as either good or bad. So just to give a brief overview as to what is this support vector machine classifier, SVM, it's an extremely powerful tool that can work on limited data sets, and it can classify data into categories. And it works by assigning them to one of two disjoint half spaces and then determining the boundary between the two half spaces. So if you have an initial input vector, which in our case, this would be our process parameters such as scan speed, layer thickness, hatch spacing, beam current. All these things are your input vectors that describe the process, and then you have them labeled by either a +1 or a -1 in this yi vector. And basically all it does is it takes for every combination, every row of your process parameters, it labels them as either a +1 or a -1, as either a good print or a bad print. And that is what is used for these values. +1 for a good surface, -1 for a bad surface. And this bad surface includes porosity and over melting. So the SVM, it generates a hyperplane that separates the two classes, and it does this by maximizing the distance between the hyperplane, and the nearest data point for each class. And we can, if we look at the figure down at the bottom, we have this dark black line going at 45 degrees. This is our hyperplane. And then we have these data points here along this line. And these are our support vectors. And these are, what it's trying to do is it's trying to find the hyperplane that has the farthest distance from the nearest point within the support vector. And that's how you know you have a good a trained model. And the way that it describes this hyperplane is through a function called the decision function. And basically what this does is it takes a weight vector and it takes the dot product of the feature vector in a very high dimensional space, and then it adds on a bias term. And when you compute this, it gives you a value from -1 to +1. And if it's less than 0, it's classified as bad surface and it will fall under the margin. If it is greater than 0, that's a good surface and your point will be classified above the margin. And then if this function evaluates to 0, you are directly on the hyperplane. And so that is how this method works. All it is simply doing is it is trying to describe a hyperplane or a surface that separates the process parameters. And this is really where this strategy shows itself, is because this decision boundary now has a physical meaning because it is the decision boundary between bad parameters and good parameters in a very high dimensional space. And this is the power of using this method. So what they did is they printed 11 cylinders of this cobalt chrome alloy, and then they took these top surface images, which you're seeing in the top right here, and then they fed these into their SVM classifier, and it takes in sample number, line energy, area energy, energy density, radius. All of these things are inputs along with the process parameters that were used to print these. And then it is labeled, it is classed as either a bad or a good print based on the continuous value from -1 to 1 that is produced by the SVM. And this is important because it's actually a continuous value from -1 to +1. It's not a binary. And because it is this continuous value, you can see what is the degree of defect formation. And then since it is continuous, we can map it as a heat map. And that's exactly what they did. So they take the 11 prints that were used for training, and they basically plotted what are the process parameters. So we take current versus scan speed shown in figure A. And then what's shown in the triangles and dots is the training and testing data. And so for every one of the training and testing data points, there is an associated value of somewhere in between -1 and a +1 that was created by the decision function. And then you can plot this as a color scale across your process parameters, and you can see exactly where this decision boundary is occurring at this light region around 0, 0. And you can see that there is actually a region that separates the bad parameters from the good parameters, and your good parameters would be in the dark blue region. And now they showed this for many different parameters. So line energy, area energy, energy density versus scan speed. But the authors point that for an industrial relevancy, if you were to hand one of these maps to an additive manufacturing machine operator, the most powerful one would be map A, because these are direct process parameters and you can simply pick a point on the graph and extract those parameters and throw them into your machine and start printing. Whereas if you provide them B through D, there is some back calculation that is required to go from a line energy or an area energy to a beam current. So they're going to be focusing on figures A. And now, an important thing when you're talking about machine learning is hyperparameterization. If you do not tune the parameters of if you do not tune the hyperparameters of your machine learning model, I should say, you really need to do it. It's very important and has drastic effects on the accuracy of your predictions. And for support vector machines, a very impactful hyperparameter is the cost function C. And basically what this value does is it tells it how much do we want to maximize the support vector, so the distance from the hyperplane to the first data point in both directions. How much do we want to maximize that, and then how much do we want to penalize misclassifications? Because you can take a low cost function, so say C equals 0.1 as shown in figure A, And this very low cost function, it allows for some misclassifications so it can maintain a very large margin, which this is good. You would want this because it helps with generalization. So overall, your model is more accurate, taking into consideration all of the predictions of all of the individual data points. So the overall trend, it is better at predicting global trends. But if you look at the individual accuracy of single data points, it is slightly lower because it is allowing for some misclassifications. And then a high C, if we say, for example, C equals 100, this prioritizing minimizing misclassification. A C value of 100 basically forces the machine learning model to fit a hyperplane that accurately classifies every single data point in the training data, which leads to severe overfitting. So you want to find a nice medium between the cost functions. And that's what they did, is they evaluated how do these maps change when we change the cost function. And they found that a cost function of 5 was that provided the most accurate results for them. So here's pictures of the cross sections of the 11 cylinders they used for training. So this is important to look at because we want to be able to link the top surface to the internal features of the material. And we can see that there is a good range of microstructures and internal defects shown in their training data from figure A, E, F, and K, which look pretty good. And then there are a bunch of other ones that are classified as bad surfaces that actually have tons of internal defects. And this is how we can give a physical connection between the surface and the internal defect generation. So putting it all together, they used a cost function of C equals 5, and they generated this printability map where they plotted the speed function, which is an intrinsic property to the ArcAM e-beams that these guys are using in their study. And they found that if you plot this versus the current, it gives you the best opportunity to extract good parameters from the map. And you can see that there's a very large region of good parameters in this dark blue. And then we can see again, there's the decision boundary. This is the decision function evaluating to f of x equals 0 in this light region. And then we have the bad parameters. And there's about 9 training points within the bad region and 3 training points within the good region. So then when they selected parameters from the good region, it produced the cylinder shown in figure B here, and we can see the top surface is beautiful. The morphology is great. It's very smooth surface. There's no visible porosity, etc. And then when they look at the cross section, indeed, this is a very defect-free part that was printed. And then when we look at a magnified image, we can see that there are a few internal defects, there are a few pores, but it is significantly lower than any of the other printed parts. And they came to this conclusion with only printing 11 cylinders. This was the 12th cylinder that was printed in the study, and it was beautiful. So this really goes to show the power of using this kind of technique when you are trying to optimize process parameters. So bringing it all together, what did we learn? So in this work, they really highlighted the ability of a support vector machine to perform under sparse data conditions because they only had 11 data points, which if you talk to anyone in machine learning, that's not a lot of data. And through this method, the time to optimize parameters is orders of magnitudes quicker than with other strategies. And this method, it's material/machine agnostic. It can be applied to any AM process and determine the optimal processing window. So no matter what type of machine you are, as long as it's a powder bed process, that's important, and metal AM, and no matter what is the metal, the material that you're trying to print, this theoretically should work. This is what the authors state, that it's an agnostic, and that's one of the biggest benefits. And then the coolest thing is that they actually put a physical meaning to this decision boundary. It is literally the boundary in the high dimensional process parameter space between combinations of parameters that produce bad prints and good prints. So it is a physical boundary in this high dimensional hyperspace. And that to me is really cool. And with that, I thank you for your attention. Um,